There you go. Okay, so now we're recorded, and you guys should be able, I hope now, to see the stress strain curve. This is actually real data taken by one of my students for well we'll see in a second, but for a real sample, not having anything to do with the CPU cooler, but if you knew the material of the CPU cooler, I'm thinking that it's aluminum again, but I'm not sure. You could back out or look up a stress strain curve for that material, and then you can conduct all of these same analyses that I'm about to show you here using the curve. So let's just walk through this as kind of an example to get us up to speed for DML and MEC1. Okay, so the first question that I asked you was, you've got the stress strain curve, but you don't know the material. You do know, however, that it's either a brass alloy or a ceramic. Which material do you think it is? And explain your reasoning. So what do you guys think? Is this ceramic or brass?
Brass.
Yeah. Okay. It's brass. And why brass?
Because it looks like the stress strain curve for a ductile material.
There you go. Perfect. Yeah. It's ductile. It's not brittle. So hence brass over ceramic. Perfect. Okay. Next question is, find the yield strength in SI units. Okay. And the good news is that everything is already in SI units, so we don't have to worry about conversion. Okay. And so where exactly is the yield strength? Well, it's the point where you basically get away from plastic deformation and into, away from elastic deformation and into plastic deformation. And the way, at least that I've seen this done, and you guys might have something more sophisticated than I do, but there's something called the 0.02% offset, because there's like a little bit of like, is the yield point here? Is it here? Like, is this really in the plastic region? It's sort of not entirely clear kind of where that cutoff is. And so the way that this is done, at least the way that I've seen it done, is to take the stress strain curve where you're clearly in the linear region, right? So like there, and just offset everything to a strain of 0.002, which again is at 0.02%, using that same slope. And so I'm going to I'm using my ruler here to sort of keep the slope as similar as I can. I'm going to start here, and I'm going to make the same line, at least a similar slope. And then I'm going to denote this spot as my point, as my yield point. So, and then I'm going to kind of move over here. Yeah, maybe it's a little bit lower than that here. Yeah, okay, maybe 275. So I'm going to say that the stress associated with yield is approximately 275 megapascals, and that's again using 0.02% offset method. Okay. Next, we're wanting to, and I should mention, I didn't mention this before. If it wasn't clear, let me mention it now. This is a single curve, but what I'm doing is, let me change colors here for a second. I'm showing you guys the inset. So this inset that I'm boxing in green right now is basically here, right? It's just this first section of the curve, but I've blown it up so that it's easy for me to kind of show like angles and where the yield point is, and the 2%, 0.02% offset and so forth. So they're part of the same curve. One is just a blown up version of the other one. Okay, so the next question is, find the fracture stress in SI units. Okay, so fracture stress is when the material actually breaks. And so that happens here, right? So that's the end of the stress strain curve, is the point of breakage. And then I'm gonna again just use my ruler and draw all the way back and try to draw a straight line if at all possible. Let's see here. To right about there. Okay. And get a result of approximately maybe about 340 megapascals for fracture. So let's see, let me put this over here. So here's my yield, is approximately 275 megapascals. And then my fracture or failure stress is about 340 megapascals. Okay. Any questions so far? This should be hopefully I'll review of mechanics and materials stuff. Let me get rid of this because it's in my way. Okay, I think we're good so far. Okay, let me get back to my pen. Okay, and this, by the way, again, is using the 0.02% offset method. Okay, the third question. No, sorry, this is the fourth question, right? So number one was what's the material? We said it was brass. Number two is what's the yield? Number three is what's the fracture stress. Number four now is calculate the modulus of elasticity in SI units. And so for this one, we need a little bit of calculation. So here's modulus of elasticity. And we know the slope of or what we're trying to find is the slope of the linear region, right? It's basically Young's modulus is the modulus of elasticity. And so I'm going to go to Hooke's law, which is that modulus of elasticity multiplied by strain is equal to a stress in the linear region. And now I can reorganize this guy like so, and calculate from the graph itself a stress and a strain in the linear region. And so I'm going to try to pick a point that sort of lines up nicely, and I'm gonna grab this point right here that lines up nicely with kind of two main axes. And so I'm going to go there. I'm going to go there, and so I've got the strain at that spot is about 0.002, right? And it's a unitless because strain is a ratio of elongated length to basic length. And then the stress at that point is 150 megapascals. And so that basically now gives me the slope of this curve or the slope of this line, at least so long as I'm in the linear region. And so hence the modulus of elasticity, 150 divided by 0.002, at least when I did it, I ended up with 75 gigapascals. So that's number four. Questions about that one? Good so far. Okay. So then the next question is to calculate the modulus of resilience. And I had to look this one up because modulus of resilience is not something that I would normally use. But interestingly, it's an energy. So all of a sudden I'm like, oh, it's energy. Okay, awesome. I love energy. So the equation for modulus of resilience is 1/2 sigma squared over E. And what exactly is this sigma? Well, it's the amount of stress that the that the sample can absorb before it starts plastically deforming. And so, I mean, yes, even though we said that the yield stress is all the way up here at 275 megapascals, just to be, sort of safe and conservative, I'm going to go back to my original line that I drew in the linear region, and I'm going to try to figure out sort of where the data begin to deviate from linearity, and it's right about here, where you can see the curve starts to kind of lean over, whereas the line keeps moving straight. And so I'm going to calculate my modulus of resilience kind of based on the strain at that spot, because that's the place where I'm still entirely sure that I'm in the linear region and I can absorb all of the energy that I put into the sample without any plastic deformation. So I'm gonna just refer to this as sub LR for linear region. And I'm going to say 200 megapascals squared divided by my Young's modulus, which is 75,000 megapascals. And I forgot the factor of 1/2, so I'll put it out there. So there's the factor of 1/2. And when I run through the numbers, I get that this modulus of resilience is 0.2667 megajoules megajoules per, hang on, let me erase, cubic meter. So in other words, at least the way that I would think about this as a guy focused on energy, is that's the amount of energy per unit volume that the material can absorb before it starts plastically deforming, which in a way is sort of interesting because a very brief and quick war story. So I'm my main area of research is Tesla turbines, and Tesla turbines are known to spin at very high RPM and very low torque. And as a result, you end up with these discs in the turbine that are spinning like super fast, and they have a tendency to like explode because they're spinning so fast. And so, interestingly, this resilience modulus is a way to sort of figure out like how much those disc blades can be, like how fast they can be spun before the centripetal force gets them to the point of plastic deformation, where you're spinning them so fast that they deform and then they get to the point where they can explode on you. So that's an interesting, kind of application of that number that would be useful for those of us in the energy field. Okay, so number 6 is find the maximum axial load that can be sustained without any permanent deformation by a cylindrical specimen having a cross-sectional area of 50 square millimeters. Okay, so for this guy, I'm going to go to my definition of yield strength. So yield strength is, it's just it's a pressure, right? So it's a force divided by an area. This is the area that I'm given, that 50 millimeters. And this force is the force that I can apply to the sample before it starts to yield, right? So again, the maximum axial load that can be sustained without any permanent deformation, permanent meaning plastic deformation. So I'm just going to reorganize this, and I'm going to say, okay, this is the yield strength multiplied by this area that I have is equal to whatever force it can sustain. And if I plug in the numbers, I got 275 megapascals is my yield strength, multiplied by 50 millimeters squared. And I get, hang on, this one I didn't calculate, 275 times 50 times 50. Okay. Oh, sorry. Let me go back. I don't actually need to square this. I was thinking diameter. The area is already given. So it's 200. Let me try again. 275 times 50. Okay. Gives me, it works out. That's an eraser. There we go. Okay, it works out to be 13.5. I'll make sure you get the units right. Newtons. If I do all the unit cancellation, so 13.5 newtons is how much force this. We know it's brass. This brass sample can kind of absorb before any sort of plastic deformation. So, is that good? Any questions on that one? Nope. Okay, we'll probably have time to do about one more here. So that was question 6. Question number 7 is if an axial load of 325 kilonewtons is applied to the specimen, a specimen of this material with a cross section of 10 square centimeters, will it neck? And we're asked to explain. And so there's sort of 2 steps here. One is I want to, for necking, right? Necking is a failure mode. I want to check whether I'm in the plastic region or the elastic region. If I'm in the elastic region, which is below the yield stress, I'm fine. There's not going to be any necking. If I'm in the plastic region, which is above the yield stress, there's the potential for necking. And so I'm gonna, for number 7, I'm going to calculate first the stress that's on the sample given the information provided. So it's 325 kilonewtons divided by 10 square centimeters. And I end up getting that the stress is 325 megapascals. And so the good news is that I'm not above the fracture strength. So this thing, at least the way that I've loaded it, won't actually fail. It'll plastically deform, but it won't fail catastrophically. But I'm definitely out of the elastic region, right? So it's definitely going to deform plastically and be damaged. So for most situations, that would be considered a mechanical failure. So I'm actually out here somewhere, right? I'm right about here. So then the question about necking is normally what's necking. It's when you've got your dog bone and you've got it in your tensile tester, and all of a sudden the cross-sectional area of the dog bone starts to get smaller as a result of the plastic deformation that's caused by the tensile stress that you're putting on it. That necking, this sort of shape, is characterized by, here's your elastic region, and then here's your plastic region. That's usually considered the ultimate strength, and then here's where you get necking. So in this case, because the curve is always continuing to move upwards all the way until we get to the failure point, there was no necking in this sample. It just ruptured. It just failed before any necking occurred. So based on the shape of the curve, we can say that yes, it failed by deforming plastically, but did not rupture as a result of necking. So okay. So any questions about that one? Okay, cool. So I'm actually a couple minutes over. So let me I just wanted to wrap up. So let me stop there. And I'll leave the last 2 of these. Maybe we can do these last 2 questions the next time we get together before we jump into the next lecture. But that's the official end of class. So I'm happy to stick around and answer any mechanics and materials type questions related to stress strain curves that you guys have got. Otherwise, we'll see you on Thursday. Thanks for sticking around.
Thank you.
Yep, no problem. And if you guys have got just sort of class housekeeping related type questions, I'm happy to answer those too. Just let me know before you ask those, and I'll stop the recording. But I wanted to, if there were any stress strain questions, capture those for the recording. Nope. Okay, in which case let me stop recording.